Hydroboration followed by oxidation. Borane and substituted boranes adds to alkynes exactly in the same way as it would add to alkenes. That is, boron is going to act as an electrophile, whereas the hydride ion is going to act as a nucleophile. And when the addition reaction is over, aqueous sodium hydroxide and hydrogen peroxide were added to the reaction mixture, and the final result is going to be an alcohol in the case of alkenes, whereas it's going to be a ketone or an aldehyde in the case of alkynes. So when alkenes undergo hydroboration followed by oxidation, it's going to give us alcohols, whereas alkynes, when they undergo hydroboration followed by oxidation, it's going to give us a carbonyl compound. So it could be a ketone or aldehyde, depending upon whether it's a terminal alkyne or internal alkyne. When you take a symmetrical internal alkyne and subject it to hydroboration followed by oxidation, it's going to give us only one product. So this is a symmetrical alkyne, symmetrical internal alkyne, which is giving us only one product. But when you take an unsymmetrical internal alkyne and subject it to hydroboration followed by oxidation, it's going to give us two products. So in the hydroboration followed by oxidation, what's going to happen is the BH2 or Br2 is going to get added to one of the carbons, and the hydrogen ion is going to get added to the other carbon. And the next step where the oxidation happens, the BH2 or the Br2 is going to get converted into OH, giving the enol. And once we get the enol, we know that it's not going to be stable, so it is going to get converted into the keto form. Okay. Now, why in the case of unsymmetrical internal alkyne it leads to two different products? So this is going to exactly look like the same thing as what we have done in the case of acid catalyzed hydration of an alkyne, where it gave two different products for an unsymmetrical internal alkyne. So to begin with, the unsymmetrical internal alkyne is going to undergo hydroboration reaction where it's going to form two different alkenyl boranes. Here are the two alkenyl boranes that has been obtained for this unsymmetrical internal alkyne. So these two alkenyl borane is going to undergo oxidation to give us the two enols, and from there it is going to get converted into the keto form. These are the two enol structures, okay, and from here it is going to get converted into the ketone. So you can see that this is 2-pentanone and this one is 3-pentanone. So on the whole, when an unsymmetrical internal alkyne is subjected to hydroboration followed by oxidation, it's going to give us two different products. When terminal alkynes undergo hydroboration followed by oxidation, it's going to give us an aldehyde and not a ketone. Now, why an aldehyde and not a ketone? Because here Markovnikov's rule is going to be followed because one of the carbons has got an hydrogen here. So the electrophile, which is Br2 or BH2, is going to get added to this carbon, which has the highest number of hydrogens, and the hydride ion is going to go to the other carbon, right? So this is going to lead to the formation of an enol, and since the enol is not stable, it is going to get converted into the keto form, and therefore it forms an aldehyde. So this is going to be the main difference between the acid catalyzed hydration of an alkyne and hydroboration followed by oxidation of an alkyne. So in the acid catalyzed hydration of an alkyne, it is going to lead to the formation of a ketone, whereas with the hydroboration followed by oxidation, it's going to lead to the formation of an aldehyde. So terminal alkynes will form aldehydes, whereas internal alkynes will form ketones. Also, in the case of terminal alkynes, we have to use highly sterically hindered boranes such as 9-BBN in order to prevent the terminal alkyne from undergoing a second hydroboration reaction. Whereas in the case of an internal alkyne, the substituent which is present on the carbon which has a triple bond is going to prevent the alkyne molecule from undergoing a second electrophilic addition reaction.